Hey guys, last video got cut short, so this is split into two. This section that was going to be pretty quick and easy. This is called the natural logs section. So we just talked about common logs. Common logs have a base 10. Natural log looks like this. ln of x. And that's exactly how you say it. Well, actually, you don't say it like that. For whatever reason, mathematicians put ln instead of nl to talk about the natural log of x. So I don't know why, but that's the way it is. I write mine in cursive. I just kind of just taught that way and it stuck. You don't have to write it in cursive, but I do recommend, if you write ln, this kind of looks like one in. So at least write, a little curve to your L or something to show that it's ln. And then sometimes you'll see people put, just even like with logs, put the contents on the inside in parentheses, but not all the time. So basically, kind of like common logs, natural logs have an understood base. And here's what we got. If you have log base e of x, then this is the definition of a natural log of x. So essentially, it is just a log with base e. So those are the two, commonly used bases. Is your common log of 10, and then sometimes we'll use a base of e for natural log. So we're just going to do a few examples of different things that you could do with natural logs. And I'm going to start my numbering system over again since we're now on natural log. So we're going to go ahead and, number one, I want you to evaluate the natural log of 1 over 0.32. Not sure why we're trying over here. And essentially, in your calculator, you use the natural log button, which is right by the log button. It's right below it. It says ln. So if I want you to evaluate this, you literally type, you hit the ln button, and you put 1 over 0.32, and you'll get approximately 1.1394. That's that. Now, the next thing I want you to do is type in your calculator, evaluate the natural log of e. So you'll hit natural log, and then the e button, remember, is on the division symbol. So you hit the natural log, and then you'll hit second division symbol to input the natural log of e. And then when you hit enter, you'll find something very lovely occurs. And you'll find that the natural log of e is equal to 1. And I want you to think about why this is. If the natural log is defined as a log with base e, then I could rewrite the natural log as log base e of e. And if I'm like, okay, what does that equal to? When you convert this to exponential form, you get e to the x power equals e. And this is true when x is equal to 1. Now, this is another big takeaway. And this is why you're going to notice we're going to do a lot of the same things with natural log that we did with common logs. And you might wonder, okay, which one should I do? Should I do the common log or should I do the natural log? And basically the rule of thumb is if you have e in your problem, natural log is the way to go, because sometimes you'll be able to cancel things out by doing this. The natural log of e is equal to 1. So before we get to solving, though, I want to do some other types of problems, just like we did with common logs. I want you to use change of base. Use change of base to evaluate. So example 3, if I give you the log base 5 of 132. Now, in the last video, when we talked about common logs, the change of base for that would have been, okay, then we just take, log of 132 divided by the log of 5, and we're done. Well, using change of base with natural log is the same exact thing, except instead of taking the log of 132 over the log of 5, which is, understood base 10, let's just understand that the base is e, because we can make the base whatever we want, and then use the natural log of 132 divided by the natural log of 5. And you would get the same answer even if you did the log of 132 divided by the log of 5 because of the exponential properties. But either way, you should end up with approximately 3.0339. So we could do the same things like we did with common logs with natural logs. Now, again, I think the bigger questions that we're going to be dealing with are solving questions. You can probably tell Harrison is in the background of this video. Maybe it'll bring you some joy. Yes, I just said your name. Go away. Go play. Go play. Go see Mickey Mouse. All right, number 4. I want you to solve 3 to the 2x power is equal to 7 to the x minus 1 power. Now, you don't have to use natural logs. You can use common logs. You can, remember when you solve and you have something that's an exponent, you just take the log of both sides and then proceed with, regular algebraic rules. Well, here, we're going to do the same thing, except I just want to use the natural log just because. So if my exponent, or if my variables are in the exponents right now, I'm going to go ahead and take the natural log of both sides. So the natural log of 3 to the 2x power is equal to the natural log of 7 to the x minus 1 power. And then our exponent rules still apply. So like the logarithmic rules, if I have the natural log of something and then it's to a power, then these powers by rule drop down up front, leaving us with 2x times the natural log of 3 equals, in parentheses, x minus 1 times the natural log of 7. And then again, our goal is to isolate x. Well, again, we're in that scenario where we have x's on both sides. So what we're going to need to do is take 2x times the natural log of 3. We need to distribute this natural log of 7 to both of these terms so that we have the natural log of x minus the natural log of, x times the natural log of 7 minus 1 times the natural log of 7. We don't have to write that one. And then we want to go ahead and put both terms with x's on one side. So now I want to go ahead and subtract x times the natural log of 7 from both sides so that both terms with x's are on the left side. And then you could factor it all in one if you're ready to go. Like if you're in kind of understanding of that. Otherwise, just write out what you have. 2x times the natural log of 3 minus x times the natural log of 7 is equal to, do not forget about this negative symbol, natural log of 7. And then from here, we can go ahead and factor x from both sides. My son is screaming because he put all of the golf balls in the bag and now he can't get them out. Welcome to the life. So now we can go ahead and factor the x's out of both of these terms, leaving us with 2 times the natural log of 3 minus the natural log of 7 equals negative times the natural log of 7. And then to isolate x, I can divide both sides by all this stuff that is stuck to it. In parentheses, 2 natural log of 3 minus natural log of 7. I'm dividing 2 natural log of 3 minus natural log of 7. So when you divide this, again, be very, very careful. This yellow expression is what you need to be typing in your calculator. Be extremely careful, and I'm going to give you guys a second to type this in to make sure that you're entering this stuff in correctly using parentheses for that expression that's on the bottom. Also, don't forget about that negative symbol. Negative natural log of 7 divided by all of 2 natural log of 3 minus the natural log of 7. When you do this, you should get that x is approximately negative 7.7433. Now, there was really no purpose in using natural logs there that was any more beneficial than using common logs. Like we could have taken the log of both sides and gotten the same exact answer. There are, however, some examples where using natural log is better, such as this, example number 5. 4.5 is greater than or equal to e to the 0.031 t power. So again, I mentioned anytime you have anytime you have e, natural log is going to tend to be your better option. And here's why. And again, this is an inequality, but when you solve inequalities, it's the same as solving with equations. The only thing you have to be mindful of is if you end up dividing both sides by a negative, you have to remember to flip your sign. That's not going to be the case here, but you may run into one like that in the future. So I want to go ahead and take the natural log of both sides. So I have the natural log of 4.5 is greater than or equal to the natural log of e to the 0.031 t power. And side note, guys, I don't think I did a great job of explaining this earlier because my brain kind of got ahead of me. But essentially, you know, your natural log and your logs are the inverse operations of exponents. So when you solve an equation and you're trying to undo something, we do the inverse, right? If something's being multiplied and we want to undo it, we divide. If it's being added and we undo it, we subtract. So if I have something raised to an exponent and I want to undo it, I'm going to take the log or the natural log of both sides. So there's nothing to do on the left side, so I'm going to leave this part as the natural log of 4.5. And then on the right side, again, I can apply that rule, right? My exponent's going to come down out front. So then 0.031t times the natural log of e. So here's the beauty of using natural log with e. Earlier, we said the natural log of e is equal to 1. So then that term just straight up cancels. There's not much left to do. If I want to isolate t, I can just divide both sides by 0.031. So in your calculator, you're inputting in this yellow expression, natural log of 4.5 divided by 0.031, and you should end up with 48.5186 is greater than or equal to, the only thing we have left on the right side is t. Or you can say, you can switch it around. T is less than or equal to 48.5186. So again, natural logs have the same capabilities as common logs do. And it really doesn't matter which one you use under a given circumstance. Heck, you could have even used a log. You could have used the common log to solve this. You would have just had to input a little bit more in the calculator because this natural log of e would not have canceled. But there's benefits of using natural log, benefits of using log and other common logs in other scenarios, but essentially they hold the same purposes.